All right, our topic for today is properties of the cross product. We looked at the cross product for the first time in the last lesson, having already done the dot product, and we said now we've got this new vector idea called the cross product. And cross product was kind of special because what it would do was actually take two vectors and then produce a new vector. And the rules for the cross product was sort of twofold. Remember, the direction followed the right-hand rule. So if you pointed your arrows towards the first vector, curled your fingers through the angle in between the vectors towards the second, your thumb pointed to in the direction of the cross product. And the other part was the magnitude, and the magnitude of the cross product was always equal to the area that the area of the parallelogram that we would have got had we actually created a parallelogram out of the two vectors. And that was all definition again. Remember, we just defined the cross product to be that. So we want to look at some properties today. Sorry, by the way, remember those definitions really were what we used from a geometric standpoint. We used our little shortcut calculation to be able to calculate the cross product in Cartesian form. And that's much more common for the type of questions that we're going to have to do. This is going to be an important idea for us from a three-dimensional standpoint. It says two vectors are collinear if they're in the same or opposite directions. We knew that. We've done two-dimensional stuff before. So for example, there's a vector and there's a vector. They're not perfect, obviously, but assuming they were parallel, we would say they're collinear vectors. Even if we had one going in the opposite direction, if they're parallel, we'd say they're collinear. And that's important because if you have two vectors that are collinear, that's still only going to allow you to move in one direction, right? I guess maybe two, right? One direction and the opposite direction. That's different from saying vectors are non-collinear. If we have, say, this vector and then this vector, non-collinear vectors were much more useful. And we talked about that in previous units, in the last unit, with the idea that if I used so many of the first vector and so many of the second vector, I could create any other vector that I wanted. Okay, that idea is going to work in 3 dimensions as well. But instead of thinking of things being collinear, now we're looking at the idea of something being coplanar. So 3 vectors are coplanar if they all lie in the same plane. Now, we've talked about this a little bit as we've gone. One of the tricky parts now isn't going to be all the calculations we have to do, but trying to picture things. And I tried to get the video here so that I could actually show you some stuff, but it's not working just yet. So I'm going to do my best to try and describe some things. And if you have some, honestly, if you have some pencils or pencil crayons or something, it will help. 3 vectors are coplanar if they all lie in the same plane. The easiest planes for us to picture are the floor and the walls. Right, and they're nice and easy. They're all perpendicular to each other, which kind of simplifies things a little bit. But if we're talking about 3 vectors being coplanar, what that would look like is if you took 3 pencils and just laid them all on your piece of paper or laid them all on the floor. Okay, they're all on the same plane, and that's now the 3-dimensional equivalent to collinear vectors. Okay, if you have 3 vectors that all lay on the same piece of paper, then there's no way for me to move off the paper. I can use a few of those different vectors to move in different directions, but no matter what, I'm stuck on the paper. So where I'm right here now in the note, it says this is true if you can write one vector as a linear combination of the other 2. And that's as we've done this already. We've said if I have, say, this vector, I'm now actually going to imagine the board is the plane. So I'm not trying to draw anything in 3 dimensions here, okay? There's one vector, here's another vector, and here's a 3rd vector. Those vectors are all flat on the screen, right? They're all coplanar. And what we're saying is that it's possible to write vector u, maybe call the blue one vector u. It would be possible to write that in terms of some vector v's and some vector w's. So I'd need a certain number of each, but I should actually be able to create that new vector, or maybe I might have to use some negative numbers for j and k, but one way or another I could try and, I'm trying to picture it right now how it would look. I think I could, if I make that quite a bit bigger, and if I take this vector and flip it around so it's going the opposite direction and make it bigger, this isn't going to be perfect. Well, it's almost close. Maybe you can see how it would at least be possible that I could get, oh, it's closer, that I could use a certain number of the red ones and the green ones. Wow, I came close to create that blue. And it looks like I have to shrink everything down a little bit more. All we're saying is, I've never tried this before. Oh, look at that, came close. So I never changed the blue one, right? But I moved the green one and the red one a little bit, just scaled them up, scaled them down. So a certain number of vector v's and a certain number of vector w's would allow me to create vector u. And so we say those are coplanar vectors, if that's possible. And so here's a big note. If u, v, and w really are coplanar vectors, so that's the situation we see here, right? The blue, the green, and the red vector. If they really are coplanar, then u cross v, the cross product of two vectors, would have to be perpendicular to the third vector. Okay, if I pick any two vectors and take the cross product of them, they'd have to be perpendicular to vector w. And this is what I need you to try and picture for me again. So I need you to grab, probably try doing 3 pencils and a pen maybe, but you need 4 things, okay? So on your piece of paper, take the 3 pencils and just lay them all flat. So on your piece of paper, it would kind of look like this, one like this, one like that, one like that. It might be easier actually if you line them all so that the erasers are all touching. And just to try and simplify things a little bit, I'm going to call this vector u vector w, and I don't know what's easier. U, this is v. This works no matter how I label it, but I think it's going to be easier for you to picture if I do it that way. There's vector u and vector v, and then vector w. And they're all coplanar because they're all flat on this page, okay? What we're saying is that if they're coplanar, then u cross v is perpendicular to vector w. So what you got in front of you, I hope, is those 3 pencils that are all flat touching at the erasers. Take your pen, and the pen is going to represent the cross product. Okay, we're not going to get the magnitude, right? All I care about is the direction. If we want to do u cross v, the way you did that was you pointed your fingers along the first vector, and you curl your fingers towards the second vector, and whichever direction your thumb points is where the cross product is. So if you do that right, your thumb should be pointing out of the page or out of the board, which means your pen, if you've got all those pencils laying right there in front of you, your pen should be sticking straight up, pointing at the ceiling. Okay, again, I don't care about the magnitude, all I care about is the direction. So the cross product is pointing straight up. Well, if it's pointing straight up and vector w here is flat on your page, then w, that third pencil, and the cross product, which was your pen, would have to be perpendicular, aren't they? One's going straight up and one's flat on the desk. So we're going to end up in that situation where our cross product is perpendicular to the third vector. Okay? Again, this is only true if you have coplanar vectors. Only if you have coplanar vectors. And that's, I don't know, I hope that went okay. If you're having trouble picturing some of this stuff, come and see me, because I'm not claiming that it's easy to picture. I honestly have a whole bunch of, I have some TV antennas, and they work relatively well to help demonstrate some of this stuff in 3 dimensions. But it's not a silly thing to have all these pencils out there and try and actually hold them and try and orient them. It will help. That idea now leads to this, our test for coplanar vectors. So if we have vector u, vector v, and vector w, in R3, so three-dimensional vectors, and they have to be three-dimensional vectors because I'm going to do a cross product. It says if u cross v dot w is equal to 0, then the vectors really are coplanar. And that's what we just said, right? If the vectors were coplanar, then if I do the cross product of 2, it should be perpendicular to the third vector. Well, the way you check for perpendicular, right, vector A is perpendicular to B if and only if the dot product was 0. Well, that's what I'm doing here. I've found one vector, u cross v, and I want to check to see if it actually was perpendicular to the third vector. If it was perpendicular to the third vector, we get an answer of 0. And if that happens, the only way for that to have happened was that all three vectors were originally coplanar. Okay? If we get any answer other than 0, anything else, I don't care what the number is. It makes no difference what the number is. As long as it's not 0, then the three vectors are not coplanar. Okay? And this is helpful. I think this makes sense. I mentioned it a second ago. The way I drew those three vectors, let me back up so you can see it again. Vector u, vector v, and vector w, I drew them there because I thought it would be easier to picture. It doesn't matter if I did u cross v and then checked it with vector w, or if I had done vector u cross vector w and then checked it with vector v. All I have to do is pick two of them, take the cross product, and then do the dot product with the third vector to see if it equals 0. The reason that that's helpful, the cross product can be a pain in the neck calculation, right? We talked about last lesson that it's very easy to slip some numbers in there. And I don't know if you noticed it or not, but a few of the examples that I did, and hopefully a couple of them that you would have noticed in the homework, have zeros in places. And if you're trying to do the cross product, if they have zeros, the cross product becomes a much easier calculation. So if you're given three vectors and you need to do the cross product, pick two vectors that have some zeros in it first. And I think I led you perfectly into that one then, didn't I? Determine if vector A, vector B, and vector C are coplanar. So there's A, B, and C. If they really are coplanar, if they're coplanar, then I could take two vectors, find the cross product, and then that cross product would be perpendicular to my third vector. If it was perpendicular to the third vector, then the dot product would equal 0. So I need to take the cross product of two of these and then do the dot product with the third vector. What I was just saying is I'm better off picking vectors that have zeros in it. So my test, I'm going to check to see if vector B cross vector C, that'll give me my cross product, a perpendicular vector, is it actually perpendicular to vector A? And if it is actually perpendicular, will it equal 0? Okay. So if it equals 0, the vectors are coplanar. If it does not equal 0, then they are not coplanar. Cross product. Vector B, remember our trick, we start with the second component, and we have to write the second component twice. Here's vector C. And so I'm going to do B cross C, and I'll dot product that with vector A. I'll write that in real quick, minus 4, 2, 1. So our cross product, down products minus up products. So here's where the 0 helps, right? 0 times minus 4 is nothing with the 0. Take away 6 times minus 2. So that's take away a minus 12, which would be a positive 12. Oh, that worked really good. That almost worked really good. Set it over to the next one. We get oh, that's pretty nice. We get a 0 there again. Minus 2 times 0 is still 0. Take away minus 4 times 3. That's another 12. Multiply that over one more. 3 times 6 would give us the 18. Take away 0 is just 18. So that's my cross products, 12, 12, 18. I want to dot product that with the third vector, the one that I haven't used yet, which was vector A. So dot product multiplying the components, minus 48, plus 24, plus 18. And what's that? 34, 42, minus 6, I think. The funny part is I couldn't care less what number it is, right? Minus 6 really doesn't matter. All that mattered was, is it 0 or not? So my conclusion is, since B cross C dot A does not equal 0, the vectors are not coplanar. Now, remember what coplanar would mean. Coplanar was all three of them were laying on the floor. Okay, it was the easiest way to picture it. I could take those 3 pencils and flip them in lots of directions. If I could still take a piece of paper and put the piece of paper over all 3 pencils at the same time, they would be coplanar. These ones are not coplanar. So if you want to picture that, put your 2 pencils, just 2 pencils, flat on your paper again, and take your third and put it anywhere else, right? Just not parallel to the paper. So it doesn't have to go straight. It doesn't have to go straight up. It doesn't have to be perpendicular to those two. It can be anywhere else. Just it can't be laying flat. Okay? So our test for coplanar vectors, pretty important idea. A couple more properties here. These are all just true statements. So A cross B, I think this one makes sense. It says A cross B is equal to negative B cross A. So either way, we're calculating a vector. But we talked yesterday about how A cross B would give you a direction either out of the page or into the page. If I cross product it in the opposite direction, the cross product goes the opposite direction. So that's why the negative's in front. We're saying they're opposite vectors. Property 2 there is your distributive property. So you can, if you have the cross product of the sum of vectors, you can actually do the cross product of each one individually and then add it up. And third one there, if we do the cross product of the same vector, we get an answer of 0, which geometrically speaking, I think makes sense, right? We're talking about the magnitude of that should be equal to the area of the parallelogram. Well, if you're using the same vector, there's no parallelogram, so you can't have a magnitude of anything. We're going to try and prove statement number 1. And we're going to do it very formally. We're going to try and do it with the definition of cross product. Now, I told you before that you don't have to know this formula, and you don't. So if on the test or exam or whatever, I ever asked you to prove something with the cross product, I'll give you this. Okay, I don't want you to try and remember that. You could come up with it again using our trick, but that's not what I think is important. So if I ever ask you to do one of these on an in-class assessment, I'll give you the formula. Okay. We're trying to prove that A cross B is equal to negative B cross A. Well, I've got everything started right here. Here's A cross B, and the definition of the cross product was that it's equal to that. Okay, so that's the beginning of it right there. So I'm going to just keep going with that line. And as I say, what we're trying to prove is that it's actually equal to minus B cross A, which, believe it or not, this isn't a very hard proof. What's going to make it tricky is there are so many A's and B's and so many subscripts that sometimes we'll get mixed up with what's going on. So here's what I'm going to do first. Thinking about what I'm trying to prove, I've started with A cross B, and I'm trying to prove that it's equal to something with a negative in front. So the very first thing that I'm going to do is I'm just going to pull out a negative in front. And to do that, all I'm doing is I'm factoring it. I'm going to factor that negative out of all 3 of those terms. So that's going to change the sign of everything. It was positive A2, B3, now it's negative. Then positive B2, A3. Right, that was just my first component, but all of the signs have changed. Same thing here. Switch the sign on this one. It'll look like that. That doesn't seem like a fantastic step, but it's good that we've got that negative in front. Right, we were going to need that. Now I'm trying to prove now. Again, I've got the negative. Right, I need to show that it's equal to B cross A. Well, B cross A starts with vector B and ends with vector A. I'm just going to take each of these components and I'm going to change the order. Okay. So the negative term is going to come second, the positive term will come first. So B2A3, and now minus A2B3. Okay, I haven't done much, I'm just switching the order. I'm allowed to do that, or it's just numbers. We're just rearranging the order of the numbers here. B3, 1. Oops. And believe it or not, we're now done. It's just maybe not obvious that we're done. We were trying to prove that's equal to minus vector B cross vector A. And that is exactly what this is, right? If you think, go back up to this line here, which was the definition of what the cross product was, right? A cross B, A first, B second, was A2, B3. So now if I want to go the other direction and go B cross A, I'm just putting the B first and the A second. Can you see that there? B2, A3 compared to A2, B3? It's the same thing, just I've switched the order. Same with the next one. A2, B3 used to be B2, A3. Right? The letters have now switched the order, and that's all. That's all that's happened. So not a, I know it's one of those proofs that it isn't that hard, I don't think, but it is not super obvious what happened along the way. You got to be really paying attention to the details with those subscripts. Okay, one more. I should put a QED there, shouldn't I, just for kicks? There we go, QED, proven. We got it. This is the one I like. This one I like. Prove the following. Prove that A cross B, the magnitude of it squared, plus the dot product squared is actually equal to the magnitude of A squared times the magnitude of B squared. And if you can, honestly, you'd be way better right now to pause this for a minute and give it a shot. Think of this as an inquiry question on the test, because the level of difficulty is about right. Okay, this is about the right level of difficulty for a test inquiry question. You haven't seen this type of problem before. Well, you haven't seen exactly this problem before. It's a proof, which makes it tricky. And there's something you have to remember from previous grades, which is the best part of this whole one, is why I picked it in the first place. Okay, so if you can, just pause it for a minute and give it a shot, and then come back and I'll show you how to do it. All right, good luck. I hope it worked. If you didn't get it, then feel free to pause this part way through and see if you can figure it out along the way. We need to remember what the magnitude of A cross B is, and we need to remember what A dot B is. And the tricky part of this proof is that we had different calculations for it. Right? We could do it with our Cartesian formulas, or we can do it with our geometric definitions, and that's the way we want to go this time. So the magnitude of the cross product, we defined that as the area of the parallelogram, right? That was the magnitude of A times the magnitude of B times sine theta. Right? That was how the cross product magnitude was defined. The dot product was originally defined as magnitude of A, magnitude of B, cos theta. And then we discovered that you could calculate it by going A1 times B1 plus A2 plus B2 plus A3 times B3. But this is how we started, right? Well, let's go to our formula then for a second, or I guess what we're trying to prove. We had magnitude of the cross product squared plus the dot product squared. Well, now I can fill some of that in. The magnitude of the cross product is magnitude of A, magnitude B, sine theta, and that whole thing is squared. And then dot product, magnitude of A, magnitude B, oops, cos theta, and that is all squared. So if everything there is squared, inside each bracket, all those three things, magnitude A, magnitude B, sine theta, they're just multiplied together. So I can distribute that squared in. It's just the magnitude of A squared, magnitude of B squared, times sine squared theta. And same thing for the next one. And this at least looks promising, because now we've got these magnitudes squared. So that's a good sign. This is where the nice part kicks in. We've got our two magnitude squareds there, and here again, right? If they're in two places, then I'm allowed to common factor them out. So I'm going to write them in front of everything. And when I common factor it out, it's going to leave sine squared theta from the first term and cos squared theta from the second term. And this is where, again, this is why I picked this proof in the first place. It works out so nice. Sine squared theta plus cos squared theta, trig identities actually help with something. Who would have guessed it, right? We thought we were just using a whole bunch of random stuff to frustrate you guys in math all along. Well, sine squared plus cos squared gives us the 1, and that completes our proof. That was exactly what we needed, right? So it turns out in the end pretty nicely. Again, I really like that proof. Tricky part on that one was how much you really had to go in this direction, right? You wanted to use those definitions of the cross product. If anyone tried doing it with the formulas from, well, that crazy cross product one or the A1, B1 formula, you could muddle through with it, but it would be much, much harder than trying to do it this way.